Welcome to the lecture on machine independent optimizations. So, the outline of the lecture is it consists of the following topics. We will look at the global common subexpression elimination. We have seen examples of this already. Now, we will look at the algorithm itself. We will look at copy propagation. Again, we have seen examples, but not the algorithm. So, we are going to discuss that now. Loop invariant code motion, induction variable elimination and strength reduction, and then a new type of data flow analysis called region based data flow analysis. Partial redundancy elimination is also a very important optimization. We will discuss that as a separate lecture because it is fairly detailed and involved. So, what is global common subexpression elimination? So, basically we have expressions which are defined in various basic blocks of the program. Now, in a particular block such as this, for example, there is an expression y plus z. Is it necessary to recompute this expression y plus z, or can we use the recomputed value which already is available at this in this particular basic block? That is the question. So, if we are going to provide conditions to check whether the previously computed values of the expression can be used here, or if otherwise we are going to recompute it. This requires the available expression information. So, recall that we discussed available expression elimination, available expression data flow analysis a couple of lectures ago. So, an expression is available at a particular point if it is computed along a path starting from the starting point to that particular point, and the operands are not modified in between. Okay. So, if the operands are modified, obviously the value of the expression changes. So, though the expression is not said to be available. So, we assume that the data flow analysis of available expressions has been carried out and the information is already available to us. So, at in and out points of the various basic blocks. So, what is the algorithm? For every statement x equal to y plus z such that y plus z is available at the beginning of SS block. So, if the expression y plus z is computed in a block and we want to reuse the previous computation of y plus z, obvious condition to be satisfied is that the y plus z is available at the beginning of SS block. Then the expression value should not have changed. So, neither y nor z is defined prior to S in that block. So, this is also very important, otherwise the value would have changed. So, if these conditions are satisfied, so then the available expression availability of the expression y plus z at the entry point of the basic block tells us that the expression is available along every path that reaches this particular block. So, recall that the confluence operator is intersection. So, we would have made sure at the time of data flow analysis that the expression is available along every one of these paths. So, now the available expression information only tells us that it is available, okay, but in which block has it been computed, that is not yet known. To understand this, we need to to determine this, we need to search backwards from the SS block in the flow graph and find the first block in which y plus z is evaluated. So, this has to be done for every path that actually reparts backwards in the flow graph. So, we have this particular basic block. So, there are 3 paths that we have shown here. So, we must make sure that along each path we search backwards come to the block that evaluates y plus z. So, along this path again search backwards, come to the block that evaluates y plus z, and the same along this path as well. But what is important is that we do not have to cross this block and go beyond, that is not even necessary. We just have to locate the first computation along this path in the backward direction. So, if that is done, then we would have actually located 3 of these for the 3 paths, each one of them actually has evaluated y plus z. The common sense thing to do now is use the same temporary into which we want to evaluate y plus z. So, u equal to y plus z, u equal to y plus z, u equal to y plus z, and now we can here say x equal to u. But the variables k, I, k, l and m cannot be disposed of. So, we also have statements k equal to u, l equal to u and m equal to u. So, that is what is said here, create a new variable u and replace each statement w equal to x plus y plus z found in the above step by the code segment u equal to y plus z and w equal to u. Then finally, replace the statement s by x equal to u. So, this takes care of one particular common sub expression. It is probably necessary to apply GCSE again and again to catch deep common sub expressions. So, let me explain that now. So, here is another example which we have seen before, but in the light of GCSE, let us just look at it again. There is a block here a equal to containing a equal to x plus y and b equal to a star z, and it leads to another block containing c equal to x plus y and d equal to c star z. Clearly, x plus y is a common sub expression. So, let us eliminate it. So, we do that u equal to x plus y and a equal to u, and here it is c equal to u. The other 2 statements remain as they are. Now, suppose we do copy propagation. Now, we find u now b equal to u star, this a equal to u is a copy. So, the value of a here can be replaced by u, and the value of c here can also be replaced by this u. So, we get b equal to u star z and d equal to u star z, which actually are common sub expressions again. So, elimination of these gives us the more compact code u equal to x plus y, v equal to u star z, b equal to v and d equal to v. So, this is what we mean by application of GCSE repeated number of times. So, usually we apply GCSE copy propagation and GCSE again. So, in fact, it may happen that we apply all the optimizations once, but then these and then again apply it once more and so on and so forth. But GCSE and copy propagation are so closely linked to each other that we may have to apply them in pairs until no more GCSE can be performed. Let us look at a bigger example. We use this as a running example in our introduction to optimizations lecture as well. So, there are many common sub expressions here. For example, T 2 equal to I minus 1 here and T 21 equal to I minus 1. So, I minus 1 is a common sub expression. T 4 equal to 4 star j here, and then T 10 equal to 4 star j, T 12 equal to 4 star j, one more. And then we have T 6 equal to j plus 1 here, and then T 14 equal to j plus 1, T 17 equal to j plus 1, T 20 equal to j plus 1. So, there are many of, and then 4 star T 6 will be caught as a common sub expression in the second round. So, let us look at the primary sub expressions, and once they are eliminated we get this picture. So, this I minus 1 is a common sub expression. So, we have caught that here and replaced it by T 2. So, T 2 equal to I minus 1 is actually computed only once. Then 4 star j is computed in T 4. So, T 10 equal to T 4. Okay. So, we have not computed 4 star j again and again. J plus 1 is computed into T 6 here. So, we have the T this is j plus 1 is T 6. So, T 14 equal to T 6 and T 17 equal to T 6 and finally, T 20 equal to T 6. So, we are reusing the same value again and again. We did not introduce yet another temporary for 4 star j like in the algorithm here. See, for example, here we said u equal to x plus y and then a equal to u. We did not do that here because these are already temporaries. Okay. So, there was no need to, if there were global variables, we would have had to do it over and over again, but now this is not necessary. So, we use the same temporary straight away. Now, once we do this, there is a need to do some copy propagation, because you can see easily that T 10 can be replaced by T 4 here, and then T 12 can be replaced by T 4 here, and so on and so forth. So, T 15 can be replaced by rather T 14 can be replaced by T 6 and so on and so forth. If we do that, we actually would have done some copy propagation. So, let us study the algorithm for copy propagation and continue this example after the copy propagation is understood. So, what is copy propagation? Statements of the form x equal to y are called copies. Copy of y is maintained in x. Elimination of such copy statements to the extent possible is copy propagation. So, because instead of x, we are going to replace it by y itself. So, we do not have to go to x and then copy the value from x again into some other location. We are going to use the value of y in place of x straight away. So, that is propagating the copy from this point to some other point. Substituting y for x in all uses of x reached by this particular copy. There are a couple of conditions to be checked to make sure that copy propagation can be performed. First condition, the UD chain, the use definition chain of the use u of x. Okay. So, this is the copy x equal to y, x would have many uses. So, if you look at the UD chain of that particular use u of x, okay, it must consist of s only. Suppose the UD chain of some use of x had two definitions in it, then this copy s would be one of them and there would be some other statement reaching that particular use as well. In such a case, we are not certain that copy propagation must be carried out. So, we do not do it. So, we must be certain that s is the only definition of x reaching u. So, if that is so, then copy propagation can be performed, but that is not all. On every path from s to u, including paths that go through u several times. So, there could be a loop which involves u, but not s, okay, but do not go through s a second time. So, you need not go through s a second time, but you can go through u any number of times. There are no assignments to y. So, this is very important. We do not want to have any assignments to y, because the value of y would change in that case. This ensures that the copy is valid. So, if y has not changed, then there is no problem. To check this, okay, it is necessary that we formulate a data flow analysis problem, and when we formulate the data flow analysis problem, condition 1 automatically gets tackled. So, here is an optimization problem, copy propagation, and we are trying to solve that problem using another data flow analysis. So, this is something not very special, because to perform partial redundancy elimination, which is an optimization, we are going to use data flow analysis as a tool again. So, what is this new data flow analysis problem? Here the the domain of the values in the domain of the data flow analysis problem are sets of copy statements. So, the domain itself consists of sets of copy statements. C gen B is the set of all copy statements S x equal to y in B, such that there are no subsequent assignments to either x or y within B after the statement yes. So, again we have gen, kill, in and out. C gen is the equivalent of gen that we have seen so far. So, what are the copies generated by a certain basic block B? Those copies x equal to y such that x and y are not modified after s. So, that is a statement which will be in the C gen. So, if you take all such copies within the basic block whose left hand side or the right hand side are not modified, then that is the gen function. What is the kill function? This is straightforward. Suppose you have either x or y assigned in a basic block, then this assignment to either x or y kills copies in other basic blocks. So, for example, C kill B is the set of all copy statements S x equal to y. S is not in the basic block B, we are killing it, okay, such that either x or y is assigned a value in B. So, this is also quite it makes sense, because if you are assigning some value to x or some value to y, then any copy which comes to the basic block will be not useful, because it is being destroyed within the basic block. So, when it cannot pass through the basic block and retain and you cannot retain that copy, because these assignments will kill that particular copy. And then finally, let U be the universal set of all copy statements in the program. What are the data flow equations? So, here are the data flow equations. So, let us take a look at the structure of these equations and find out the usual parameters. So, we have the usual C gen, C kill, C in and C out. Then we have intersection of C out P, P being a predecessor of B, that means the confluence operator is intersection here. Is this a backward problem or a forward problem? Out B is being defined in terms of in B. So, this is a forward flow analysis problem, and this has the same flavor as the available expression problem, which also was a forward flow problem with intersection as the confluence operator. So, as in that case, C in of B 1 is 5, where B 1 is the initial block. So, no copies are assumed to enter the basic block B 1, which is the initial block, and the initialization for C out B will be U minus C kill B for all B not equal to B 1. So, you could have also said C in of B equal to U, where B not equal to B 1, that is also possible. So, we make sure that it is the universe of all statements, so that we get the maximum benefit in the data flow analysis. What is C in B? C in B is the set of all copy statements x equal to y, obviously reaching the beginning of the basic block, that is why it is C in B, along every path such that there are no assignments to either x or y following the last occurrence of x equal to y on the path. So, you are looking at intersection, of course. So, you have to look at all paths leading to that basic block. The copy must come to the basic block along all paths, that is why the intersection, and along such paths there should be no assignments to either x or y. So, if there were, then we would have eliminated such copies from the set C in B. C out B is similar, it is at the end of the basic block, copy statements x equal to y reaching the end of the block along every path such that there are no assignments to either x or y following the last occurrence of x equal to y on the path, same thing. So, this is out and that is in. So, since we want the copy to reach along all paths leading to basic block, we are taking the intersection, and now this also makes sense. The copies can be generated in the block and not killed, of course, and otherwise they could be coming from outside to the beginning of the block and not killed in the basic block. Okay. So, that is what is C out. Now, let me show you an example first before we look at the algorithm for using this data flow analysis result. There are several basic blocks B1, B2, B3, B4 and B5 here. So, B1 has S1 and S2, both are copy statements. So, C in of B1 is 5 because nothing is coming in, this is the initial block. C out of B1 is S1 comma S2 because neither of these is killed within the basic block, they are generated, and C out happens to be that itself. What about, there is no need to loop through the statements here because this is an acyclic graph, directed acyclic graph. So, one pass over the blocks is sufficient. C in of B2 will be whatever comes from here, no need to take any intersection. So, S1 S2 which is the output of the basic block B1. And what is C out of B2? It is S2 and S4. Why? You know, here we have a statement which is not a copy, okay, and S4 redefines x. So, S1 defines x and S4 redefines x. So, the copy S1 is lost, it is killed by this statement S4. Only S4 is visible at this point. So, S2 of course is not modified, not killed. So, S2 and S4 are available, or rather reach this particular point after B2. In B3, in is the same as out of B1. So, S1 and S2, and x is again killing this statement S5 is a copy killing the statement S1 which is also a copy. So, as in this, you know, C out of B3 is S2 comma S5. Okay. So, now take B4. In of B4 is this just out of B3. So, that is S2 comma S5, and out of B4 is also S2 comma S5 because it is not assigning anything to either x or z. The important thing here is this particular x, okay, can be replaced by z. A copy propagation can be performed here for this particular x. Okay, this is the only copy which is reaching here, x equal to S5, S2 and S5. S2 is a p equal to q and S5 is x equal to z, and we are using x here. So, this is the only copy which is relevant, and it can be z can be can replace x. Let us look at this. M equal to x plus 9 and n equal to p. So, C in of B5 is what comes out of this. So, that is you know, and there is one more arc which is coming in here. So, there are C in of B4 is S2 C out of B4 is S2 comma S5, and C out of B2 is S2 comma S4. So, the intersection is only S2. Please observe here that the x equal to z here and the x equal to z here, even though they are syntactically the same statement, the same copy, but they are two different copies. Okay. Syntactically they are similar, but the S4 and S5 are two different statement numbers and they are two different copies. So, since S4 reaches here and S5 reaches along this point, these two are not the same, and neither this nor that actually are in C in of B5. Whereas, the copy S2, it reaches along this path and it also reaches along this path. So, it is in the set C in of B5. So, that is how we are taking the intersection. So, this is a very important point. The syntactically the copies may look alike, but the statement numbers will be different because they are in different basic blocks and their statement numbers are all different, and therefore, we cannot say x equal to z reaches this point. Okay. So, that is very important, and then this p can be replaced by q because S2 is reaching this particular basic block. So, this is the, and x here cannot be replaced by either this or this because no copy corresponding to x equal to something reaches the in point of this particular basic block. So, now let us look at the algorithm for copy propagation, which uses the copy data flow analysis problem results. Remember, we had to check two conditions, and I said that this condition number 1 will be subsumed in number 2 during the solution of the data flow analysis problem. We already made sure of that, because whenever there is more than one definition, either x or y is assigned a value, then the previous copy is not taken at all, it is killed. So, that is how it is actually taking the condition number 1 also in it, okay, embedding condition number 1 in condition number 2. So, for each copy x equal to y, we use the du chain and find out all uses of x. Okay. So, there may be many uses of that. So, for each of these we need to check the conditions. So, how do we do that? We just check whether S is in of basic block. Okay. So, if it is already there, B is the basic block which uses to which the use of x belongs. So, we found a use at the input point of that basic block, this copy is reaching, okay, it is there. What does this ensure us? This ensures us that S is the only definition of x that reaches this block, that is condition number 1, and no definitions of x or y appear on this path from S to B. So, because it is in S in of B, C in of B, this particular condition 2 is also satisfied, the copy is valid. No definitions of x or y occur within B prior to this use of x found in 1 above. So, in other words, we should make sure that within the basic block also the two conditions hold, that is what we are checking, that whether x or y is assigned. If it is, then I cannot do anything about this use. The copy, even though it reaches the beginning of the basic block, will be modified and hence will not be valid. So, how the point is, suppose here is n equal to p, we had p equal to something here, then even though C in B contains S2, p value would be modified by p equal to something, and therefore, this n equal to p cannot be replaced by S2. It can possibly be replaced by the previous value if it was a copy within the basic block, but not by, definitely not by S2. So, if S meets the conditions above, then remove S and replace all uses of x found in 1 by y. So, this is the copy propagation. So, here is the first example. So, let us look at another example. In our running example, we saw so many copies, this T21 is here, it is a copy, right. T10 is another copy, T12 is a third copy, T4 is one more copy, and so on and so forth. There are, and then so let us see how many of these copies can be eliminated. So, we replaced one of the copies by T4, then another copy by T4, then third one by T5, T6, fourth one by T6, and so on and so forth. So, we have eliminated quite a few of these, but once we did copy propagation, now there is chance for some more common subexpression elimination. So, 4 star T6 is here, 4 star T6 is here, 4 star T6 is here. So, we can eliminate those also, and then let us assume that we do copy propagation and GCSE together. So, now we get this, okay, T15 equal to T7, T18 equal to T7, and then all the others we did some copy propagation. Now, one other round of copy propagation will give us this particular compact code. So, see that T15 is replaced by T7 and this again T18 equal to T7. So, this T7 is again a copy, right. So, that is T18 equal to T7. So, T7 can replace T18. So, that is what happens here. So, A plus T7, A T7, A plus T4, etc. So, we are not computing any common subexpressions and we are not doing making unnecessary copies. So, this is a very compact code after common subexpression elimination and copy propagation. So, these are the what we have seen so far are can be done using just the data flow analysis information. Now, we move on to loop invariant computation and elimination of loop invariant computations, rather movement of loop invariant computations. To do this, it is not enough if we do data flow analysis. we also have to do control flow analysis, discover the loop structure, which in turn implies finding dominators, back edges, natural loops and so on. Let us assume that all that is done. That is what we mean by given a loop L. We also need the UD chain and the DU chain. So, loop invariant computation, let me give you an example just to refresh your memory. So, T3 equal to address A is the base address of the array A, which is a constant, right. So, this base address is within the activation record, the offset, and it is a value which is a constant assigned by the compiler. So, T3 equal to address A is an assignment of a constant to a temporary variable, and there is no other assignment to T3 anywhere, right. So, whether we keep this assignment within the loop or we move it outside the loop, the value of T3 will remain the same. Similarly, look at T4 equal to T3 minus 4. T3 itself carries a constant value, and therefore, T3 minus 4 will also be a constant value. So, we can move T3 equal to address A and T4 equal to T3 minus 4 together as loop invariant computations outside the loop. So, they do not vary within the loop, that is why they are called loop invariant computations. They can be removed and put outside the loop. So, how do we find such loop invariant computations? So, the first round mark as invariant those statements whose operands are all either constant or have the reaching definitions outside L. So, let us take this one at a time. Statements whose operands are all constants. So, statements whose operands are all constants, this is a constant. So, T3 equal to address A is a loop invariant computation, or have all the reaching definitions outside L. So, in other words, suppose this address A is a constant and it was computed outside the loop, it is not computed within the loop. Even then actually this is a loop invariant computation. So, address A would not have been written as address A, it would have been written as some T prime equal to address A, and we would have had T3 equal to T prime. T prime is defined outside the loop, and that definition reaches this particular use here. So, that is what we mean by the definition of the variable being outside the loop and therefore being loop invariant. Then, so such computations are marked as invariant, that is the first round. Now, what about the second round? So, see, this was marked as invariant. Now, this T3 is an operand in the next one, T4 equal to T3 minus 4, and the second operand of this assignment is also a constant. So, this is also obviously a loop invariant computation, and because T3 equal to address A is a loop invariant computation. So, we have to repeat this loop many times, mark as invariant all those statements not previously so marked, all of whose operands are constants, obviously possible, have all their reaching definitions outside L, or have exactly one reaching definition, and that definition is a statement L in L marked invariant. This is what I showed you, definition is a statement in L marked invariant, that is the example which is given here. The others, the operands are all constants, have their reaching definitions outside L, and this. Okay. So, this particular loop is repeated until no new statements are marked invariant. In fact, this particular last one is the one which discovers more and more new invariant computations. Okay. So, in doing so, UD and DU chains are useful. How? UD chains are used. So, just a second, here what happens is maybe one of the operands is a constant and the other one is defined in the loop. Okay. So, like this, that is possible, or it is also possible that both are defined in the loop, maybe one of them comes from outside the loop. All possible variations are possible here, all variations are possible, that is why this loop is necessary. So, in the first round we would not have marked anything like this. Okay. So, that is why we need to go on and on until no more statements can be marked as invariant. So, why are UD chains useful? They are useful in marking the statements as invariant. So, you are going to look at the definitions for that particular use inside the loop and see whether those definitions come from within the loop, entirely outside the loop, etc., etc., and whether they are loop invariant computations or otherwise can be checked after we discover these definitions. Why are DU chains useful? They are useful in examining all uses of a definition marked invariant. So, these are basically tricks in making the algorithm run faster. Once you mark something as invariant, for example, T3, then you can look at all uses of T3, okay, and see whether they can be marked as invariant, which if they satisfy the conditions that we have shown. So, this is one simple example of how to detect loop invariants and move them from inside to outside. So, typically here is the basic block which is just outside this. Okay. So, we have moved these two assignment statements in the same order to the basic block which is preceding. If actually we had a junction point, this particular basic block was a junction point with two incoming arcs, we would have had to actually introduce a new pre-header and move these computations into that particular pre-header. So, how do you move loop invariant code to outside the loop? That is the question. This is a very tricky situation. The example that I showed you here was a very simple example and we could move very simply, but there are many conditions to be checked. Find the loop invariant computations for each statement S defining x found in 1, check. So, there are 3 conditions. So, let us look at each of these conditions and see what they mean. It is in a block, this statement S is in a block that dominates all exits of L. So, let us understand what happens if there is a violation. So, here is a a small flow graph condition, the basic block B1, B2, B3, B4 and B5. Now, the statement in basic block B3, that is I equal to 2, is what we want to consider. This is a statement which is loop invariant, right. I is assigned a value 2 which does not get changed within the loop. So, this is a loop invariant computation. The question is, can we move this to B1? Now, the condition number 2a said S dominates all exits of L. So, in other words, this particular basic block B3 must dominate all exits of L. In this case, B4 is the only exit of L. So, does B3 dominate B4? No, because all paths from B1 to B4 do not go through B3. They can go to B2, you can go to B3 and directly to B4. So, B3 does not dominate B4. Because this is not true, moving I equal to 2 to B1 will have some side effects. What is that side effect? If we actually take this original flow graph, look at the value of I taken by j in B5. Okay. So, value I equal to 1 could have travelled all the way from B1 to B2 to B4 and then to B5. So, j equal to 1 was possible. Otherwise, we could have travelled with I equal to 1, then go to B2, go to B3, now I gets changed to 2, go to B4 and then to B5, now j gets the value 2. Suppose we move this I equal to 2 to this basic block B1 immediately after I equal to 1. Then I equal to 1 is actually overridden by I equal to 2. So, the value of I permanently changes to 2, and even if we take the old path in which j would have got the value 1, now j gets the value 2 because I has changed its value permanently to 2. So, this is a change in the semantics of computation of this particular program, and therefore, any change in semantics is not permitted. This is illegal. So, we cannot move I equal to 2 just because it is loop invariant to B1. X is not defined elsewhere in the loop L. So, let us see what happens here. So, this flow graph now satisfies condition 2a. What was 2a? S dominates all exits of L. So, again we are looking at B2 not B3 this time, we cannot move I equal to 2. So, we have given up. We now consider I equal to 3 in the basic block B3. This in B2, sorry, B2 definitely dominates B4, which is the exit of the flow graph, the loop rather. So, because all paths from B1 to B4 have to go through B2. Okay. So, whether I take this path or this path, I would have crossed B2. So, condition 2a is satisfied. What is condition 2b? X is not defined elsewhere in L. I is defined here and I is defined again here, right. So, the condition is violated. Now, what happens? So, I want to move I equal to 3 to outside the loop. Okay. So, suppose I move this to outside the loop. Now, if the loop is executed twice, I may pass its value of 3 from B2 to j in the original loop. So, if we go through this I equal to 1, then I equal to 2, I equal to 3, then possibly I can become 2 again. We come here, we go back, I gets the value 3 and then I pass out of the loop and j gets value 3 corresponding to I equal to 3. So, in other words, I is getting reset to 3 every time that I go back to the header. But suppose I equal to 3 goes out and goes into the basic block B1. First time I gets the value 3. Now, if I do not execute iterate through the loop at all, j can still get the value 3. But suppose I get I back I equal to 3, come here, then pass through this particular block, I get the value I equal to 2. Okay. And now, let us say I go back any number of times, I still retains the value 2, it never changes. Whereas, in the original loop as it is written here, I would have been reset to 3. Okay. So, whereas, with I equal to 3 moved into B1, once I traverse this particular path, I get stuck with the value 2 and never changes irrespective of the number of times I execute this loop. So, there is a change, j always gets the value 2 once I travel this particular path. Okay. So, there is a change in the semantics of the loop and therefore, this transformation is illegal. The third one, all uses in L of the variable x can only be reached by the definition of x in S. So, let us see what happens. So, this flow graph satisfies condition 2a, which says S dominates all exits of L. Okay. So, we are now looking at I equal to 2 in the basic block B4. Okay. So, B4 dominates itself. So, and it is the exit. So, 2a is trivially satisfied. What is 2b? X is not defined elsewhere in L. So, we are considering I equal to 2 again in this block. I is not defined anywhere in the loop. So, 2b is also satisfied. What is 2c? All uses of x in L can only be reached by the definition of x in S. So, here is I equal to 2, this is the definition of I. Here is use of I, k equal to I, but this I equal to 1 in the basic block B1 can reach this k equal to I equal to 2 in the basic block B4 can reach k equal to I after one iteration. So, both these definitions I equal to 1 and I equal to 2 reach this basic block B6 and therefore, it is a violation of this condition 2c. So, can we now move I equal to 2 into the basic block B1 because it is a loop invariant computation? The answer is no, because there is going to be a change in the semantics of this computation. K could have received the value of either 1 or 2 in the original loop, that is very clear. I equal to 1 could reach this, I equal to 2 could reach this after one iteration. So, both values are possible for this particular k. Whereas, once we move I equal to 2 outside, I always get stuck with the value 2. So, because I equal to 1 is overwritten by I equal to 2. So, this k will always get the value of 2 and will never get the value of 1. So, there is a change in the semantics of the computation and therefore, this is also an illegal transformation. So, assuming that the transformations are legal, we check these, okay. And how do we know that if we check these they are legal? Well, the proofs of these statements are all provided in the early papers written by Ullmann and his students. So, they are all there. Okay. So, if you look up Ahoseti Ullmann's book, at the end of it there are a large number of references where the proofs, papers containing proofs of these statements are all provided. Move each statement of statement S found in step 1 and satisfying these conditions of step 2 to a newly created pre-header. Pre-header may become necessary if the basic block at the entry is a entry of the loop actually does not have a predecessor which is a simple predecessor. So, in such a case we need a pre-header. So, provided operands, any operands of S that are defined in loop 1 have previously had their definition statements moved to the pre-header. In other words, you cannot move k equal to I unless the statement I equal to 2 is also moved. That is very clear in our simple example itself. I cannot move T4 equal to T3 minus 4 ahead of T3 equal to address A, and I cannot move it in any particular in any other order except the same that is here. So, I must move T3 equal to address A first and then move T4 equal to T3 minus 4. That is what this really says. We must move the definition statements first and then move the use statements later. Now, we need to update UD and DU chains also because the information has really changed. So, this is the loop invariant code motion algorithm. Now, we come to the next optimization, which is induction variable elimination, strength and strength reduction. So, let us see what an induction variable is. So, there is a variable x in a loop L, and if that variable changes its value only through an increment or decrement operation by a constant amount. So, I equal to plus or minus k, where k is a constant. So, then it is not necessary to have just one statement which changes the value of the variable. You could have I equal to I plus 2 in the loop in one place and I equal to I plus 3 in another place in the same loop. So, there could be more than one such statement. Okay. So, such a variable is called as an induction variable. Why? If we are actually either adding or subtracting a constant to or from a variable, then the value of that variable changes in arithmetic progression. That is the reason why it is called as an induction variable. What is a basic induction variable? Variables I whose only assignments in the loop are of the form I plus minus n, where n is a constant. So, the above one was a very general statement, and it did not say that n must be a constant. It could have been I plus minus k, where k actually is incremented or decremented by a constant amount. So, indirectly I also gets incremented or decremented by a constant amount. So, that was possible here. We did not say it is plus minus, it could have been star also. So, a change is a constant amount, that is all. Whereas, the basic induction variable, the specific form is given I equal to I plus minus n. Another variable j which is defined only once in L and whose value is c star I plus d, linear function of d, is an induction variable in the family of the variable I. So, this is also an induction variable, it is just that j depends on I. So, if I is I equal to I plus 1, so 1, 2, 3, 4 etcetera are the values of I, and then j is 4 star I, then j takes value 4, 8, 12 etcetera etcetera. Again it is an arithmetic progression, but the j is defined in terms of I, therefore, this is called as a derived induction variable which is in the family of I. So, we associate a a triple ICD with a derived or derived induction variable, C and D are constants, and I belongs to its own family with a triple I10. So, this is a definition I10, whereas ICD is for any other variable which is derived from I. So, in the previous example with the 4 star I, we would have had I, 4 and 0, okay, as the triple. So, here we have a simple example T5, so if you take I equal to I plus 1, this is a basic induction variable, okay, it is incremented by 1 in this particular loop. T5 equal to 4 star I is a derived induction variable which is in the family of I. So, this is the example I have been giving. So, this has its I has its triple as I 1 0, and now T5 has its triple as I 4 0. Okay. So, that is the triple for T5. In this example, now there are many loops, there is a loop here, there is another loop here and a third loop here, right. So, you actually when we consider induction variables, we need to look at the variable and every loop that is possible. So, for example, I equal to I plus 1 and this loop, okay, it is incremented once and it is not modified in any other way. So, I is a basic induction variable in this particular loop. But if you consider the outer loop and the same I, it is still an induction variable in the outer loop also, that too a basic induction variable, because I is not modified anywhere else by, and it is this is the it is of the form I equal to I plus minus n. The same is true for j as well. J equal to j minus 1 is a basic induction variable in this loop, and it is also a basic induction variable in the outer loop, because j is not modified by any other quantity in the outer loop as well. Then T2 equal to 4 star I is based on I. So, it is in the family of I and is a derived induction variable in this loop and also in the outer loop. Okay. Similarly, T4 equal to 4 star j is an induction variable which is derived from j, it is in the family of j in both in this particular loop and also the outer loop. How do you detect induction variables? Well, easier said than done. So, let us see how to do that. We need a loop L, reaching definitions and loop invariant computation information. So, all this is necessary. Find all the basic induction variables by scanning the statements of L. So, this is fairly easy, because the structure of basic induction variables is I equal to I plus minus n. Then the derived ones are not so trivial. Search for variables k within a single, with a single assignment to k. So, k should not have been assigned more than once. So, remember even in the definition of variable in the family of I, we said j must be defined only once. So, that is what we are sticking to in this particular algorithm. So, with a single assignment to k within L having one of the following forms: k equal to j star b, k equal to b star j, k equal to j slash b, k equal to j plus minus b, b plus minus j, and then j star b plus minus a, or a plus j star a plus minus j star b, where b is a constant and j is an induction variable, either basic or otherwise. We should have already detected it, that is what it really says. If it is basic, we should have detected it. If it is not a basic induction variable, we should have already said in which family this j lies. Okay, that information should be already available to us. Please observe that we do not have b slash j, that is not a linear form. Okay, j cannot be in the denominator. So, if j is a basic induction variable, then for k equal to j star b, the triple for k is very simple, j b 0, this we already saw, j star b plus d. So, d is 0. Similarly, if you let us take k equal to j slash b, so 1 by b is a constant. So, we might as well evaluate that constant at compile time and then say j comma 1 by b comma 0, that value can be substituted here. Similarly, for others also j star b plus a, it is j comma b comma a, okay, or minus a, and so on and so forth. If j is not a basic induction variable, then there are many complications. So, let the triple be ICD, and we need to check 2 more conditions. There is no assignment to I between the lone point of assignment to j in L and the assignment to k, and no definition of j outside L reaches L. So, this I am going to demonstrate these conditions and explain them in the next class. So, this is the end of today's class. Thank you.